Every detail in this story comes from real scientific research and observation. 40 billion rocks were already moving before anyone was here to see them. The sky above early Earth was not blue, it was orange, thick with carbon dioxide and water vapor, lit from below by a surface that glowed. Something was coming. Not one thing, not 1,000 things. Hundreds of millions of impactors, some the size of cities, some the size of continents, pulled from their orbits by a shift so slow it was nearly invisible. Two gas giants drifting, by fractions of a degree, into a gravitational resonance that would destabilize everything between them. The math was already done, the collision course was already set. The only thing missing was time. A rock larger than Mount Everest struck the surface of the moon. The impact did not just leave a crater, it excavated a basin 1,200 kilometers across, 3 kilometers deep. Today we call it Mare Imbrium. Tonight you will watch it form. The water on your planet had not arrived yet, not most of it. It was coming, locked inside the ice of objects still spiraling inward, still following the new geometry of a solar system that had rearranged itself without warning. The same bombardment that scarred every rocky body in the inner solar system was also delivering the oceans. You are standing on a world that is being destroyed and built at the same time. The temperature at your feet is above 1,000 degrees Celsius. There is no sky, not the kind you know. There is only a ceiling of rock vapor, of ionized gas, of superheated steam climbing so fast it punches through what remains of the atmosphere and escapes into space. The moon is nearly 10 times closer than it will be in your lifetime. The tides at poles are 30 meters high. The day is 15 hours long. The ground beneath you has not cooled since the last impact. And the next one is already falling. You will feel the shock wave before you see the glow. You will watch the northern horizon turn white, not sunrise, not lightning, something that has no name in any language that will ever be spoken on this world, a flash that lasts 3 seconds and leaves a basin 700 kilometers wide. The ejecta from that impact will rain down on you for days. Some of it was once ocean floor, some of it will become ocean floor again. The same object that just carved that crater was also carrying ice and amino acids and the raw molecular material that in 4 billion years will be sitting somewhere in a warm room listening to a story about where it came from. And yet, 4 billion years from now, something will find a way to be alive here. Not because the bombardment stopped, because of what it left behind. You are already inside the most violent chapter of Earth's entire history, and you are only at the beginning of it. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. 4 billion years ago, the solar system was not the orderly arrangement we navigate today. It was young, unstable, and undergoing a catastrophic reorganization that would scar every rocky body in the inner solar system simultaneously. The event we call the Late Heavy Bombardment, sometimes referred to as the lunar cataclysm, lasted approximately 300 million years, from roughly 4.1 billion to 3.8 billion years before the present. During this period, The flux of large impactors striking the moon was elevated by a factor of 1,000 compared to the current rate. Every dark basin visible on the lunar surface, the ancient crater fields that ancient people once mistook for oceans, formed during this single compressed window of geological time. The cause was gravitational. Jupiter and Saturn, the two largest bodies in the solar system, drifted slowly into a 2-1 orbital resonance, meaning Saturn completed exactly one orbit for every 2 orbits Jupiter completed. This resonance acted like a mechanical pump, driving energy into the orbits of smaller bodies throughout the system. Uranus and Neptune were displaced outward. The asteroid belt and the outer planetesimal disk were destabilized. Objects that had existed in stable orbits for hundreds of millions of years were thrown inward toward the Sun, toward the rocky planets, toward Earth. Tonight, you are going back there. You are standing on a surface that is unlike anything that exists on Earth today. There is no soil beneath your feet, no loose material, no sand, no sediment, no layer of accumulated dust. What you are standing on is basaltic rock, ancient, dense, the solidified crust of a planet still in the process of becoming itself. It is not flat. The surface around you rolls in long, slow undulations, broken by impact craters ranging from shallow dishes a few meters across to vast circular scars kilometers wide, their rims collapsed inward, their floors filled with the cooled remnants of what was once liquid rock. It is a surface that has been struck and struck and struck again and has hardened over each wound and been struck once more. The temperature of the rock beneath you is above 200 degrees Celsius, not from internal heat alone, though that is still enormous, far more than what bleeds from the Earth's interior today. The heat comes from above as well, from constant, relentless bombardment. Every object that has struck this surface in the last million years has deposited its kinetic energy directly into the crust. The ground does not cool completely between impacts. You look up. The sky is not black. It is not the deep, empty darkness you associate with space. The atmosphere of early Earth at this moment is a thick mixture of carbon dioxide, nitrogen, methane, water vapor, and hydrogen sulfide. Total atmospheric pressure at the surface is somewhere between 2 and 10 times current sea level pressure. The sky above you is a dense, hazy canopy, orange-brown in color, lit from below by the surface glow and from above by a sun that burns approximately 30% less brightly than it does in the 21st century. The sun is younger, less luminous. Still, you would not call this world cold. The moon hangs above you, and it is not the moon you know. At this point in Earth's history, the moon orbits at a distance of somewhere between 30 and 40,000 kilometers, compared to the 384,000 kilometers that separate us today. It appears 3 to 4 times larger in the sky than it does now. Its gravitational pull generates tides enormous by any modern standard, sloshing the shallow lava pools and hydrothermal basins of early Earth in waves tens of meters high. The moon's surface is already heavily cratered from the earlier period of solar system formation, but fresh craters are still appearing. You have watched one appear tonight. The flash came from the lunar surface about 40 minutes ago, a white burst, visible even through the haze, bright enough to throw a brief shadow across the rock at your feet. No sound reached you. The moon is in vacuum. But the crater is there now, invisible at this distance, a wound 200 kilometers across, where a rock the mass of a small mountain struck the lunar regolith at 12 kilometers per second and vaporized on impact. The debris from that collision, billions of tons of pulverized lunar material, is already in orbit around the moon. Some fraction of it will eventually find its way to Earth. You watch the sky. You are not afraid. There is nothing in this moment that calls for fear. What you feel instead is the weight of it, the physical, enormous presence of a solar system still writing its own rules, still deciding what it will eventually become. The orbital mechanics that govern everything around you were set in motion before the first solid material in the solar system condensed out of the protoplanetary disk. The solar system formed from a collapsing cloud of gas and dust approximately 4.6 billion years ago. In the first few 100 million years, the terrestrial planets, Mercury, Venus, Earth, Mars, grew through accretion, sweeping up material from the disk in a process driven by gravity and momentum. As each body grew, the heavier elements sank toward its center. Iron and nickel migrated downward to form metallic cores. Lighter silicate rocks floated upward to form mantles and crusts. This process, planetary differentiation, is what gave Earth its layered interior structure. Earth's core formed during this period. The inner core, a solid sphere of iron and nickel, approximately 1,221 kilometers in radius, crystallized from a liquid iron-nickel alloy as the planet cooled. The outer core, still liquid, surrounds it, and the motion of this conducting liquid generates the magnetic field that shields the surface from the solar wind. Without that magnetic field, the solar wind would have stripped the atmosphere away long ago. The water would have been lost. The chemistry necessary for life would never have stabilized. The magnetic field was forming during the period you are witnessing tonight. You crouch and press your hand against the rock. The basalt is warm, smooth in some places, fractured in others, cracked by the thermal stress of repeated heating and cooling. Along one fracture line, you can see a thin vein of lighter mineral, feldspar possibly, or an early form of plagioclase, forced up from below under pressure, a crystalline signature of the magmatic differentiation happening kilometers beneath you right now, as the planet slowly separates itself into layers. Somewhere below you, the mantle is moving. The mantle of early Earth was more fluid than it is today, not liquid, but capable of slow viscous flow driven by enormous residual heat. This heat had two sources. First, the gravitational compression during Earth's accretion, the energy of all that infalling material converted to heat. Second, and more durable, the radioactive decay of isotopes distributed through the rock. Uranium-238 with a half-life of 4.47 billion years, Thorium-232 with a half-life of 14.05 billion years, Potassium-40 with a half-life of 1.25 billion years. In the early Earth, these isotopes were more abundant than they are today, and their combined decay generated heat at a rate several times higher than current values. That heat drove convection. Hot mantle material rose, spread laterally, cooled, and sank again. The convection cells were enormous, slow, powerful. Their motion may have driven the earliest precursors of plate tectonics, though the exact nature of those early processes remains an open scientific question. What is not in question is the result, a surface in constant slow transformation, reshaped from above by bombardment and reshaped from below by the relentless churning of the interior. You stand back up. The horizon curves gently away from you in all directions. You are standing on a sphere, one that formed 4.5 billion years ago, though the specific patch of basalt under your feet is far younger than that. This crust may have been extruded from a volcanic vent only a few million years ago, solidified, scarred, and now standing in the early light of an orange sky. A low, persistent rumble reaches you from the east, the sound of a volcanic province that will not become quiet for another 100 million years. The sound never peaks, it never resolves, it simply continues, the way geological processes continue, without beginning or end from any single human vantage point. The atmosphere around you is unbreathable. Carbon dioxide concentration somewhere between 10 and 40% compared to the 0.04% of today. Significant amounts of methane, which in the presence of ultraviolet radiation breaks down and reforms into complex organic molecules that rain slowly down from the upper atmosphere and accumulate on the surface. No free oxygen, not yet. The oxygen that fills your lungs every night as you fall asleep, the oxygen that supports every breath of every creature that has ever lived, did not exist in this atmosphere. It would not exist for another 1.5 billion years, produced slowly by the first photosynthetic cyanobacteria, released as a metabolic byproduct, accumulated over hundreds of millions of years until the atmosphere reached something approaching its current composition. That transformation is impossibly far away from this moment. You are in the time before oxygen, the time before bacteria, before oceans, before continents, before any structure on this surface that would survive long enough to leave a record. And something is changing above you. You feel it before you see it, a subtle shift in the quality of the air pressure, a barely perceptible drop in temperature that lasts only a moment before the residual warmth of the rock reasserts itself, and then the sky brightens. Not all of it. A patch to the north, low on the horizon, flares to a white that cuts through the atmospheric haze, a brightness that exists at a different scale from anything you have seen in this landscape. You do not shade your eyes, you watch. The flare lasts 3 seconds. Then it fades to a deep orange glow that persists and grows and begins to fill the northern sky like a second horizon of fire. Something has struck the surface approximately 800 kilometers to the north. The physics of what just happened in the first milliseconds of contact are specific and extreme. An object likely between 5 and 20 kilometers in diameter, likely a fragment of a destabilized asteroid, moving at somewhere between 15 and 40 kilometers per second relative to Earth's surface, made contact with the basaltic crust and vaporized, not shattered, not cratered in the way a slower object would. The kinetic energy was so large and was deposited so rapidly that both the impactor and a significant volume of the target rock were converted to plasma instantaneously. A shock wave propagated outward through the crust at several kilometers per second. The immediate crater, the transient cavity, in the language of impact physics, collapsed under its own weight within seconds of forming, the walls of superheated rock flowing inward like a viscous liquid, leaving behind a complex crater with a central peak and terraced walls. The ejecta plume from the impact is now climbing through the atmosphere above the impact site. Billions of tons of vaporized and liquefied rock moving upward at velocities exceeding the speed of sound, some of it already above the stratosphere, some of it already approaching orbital velocity. Material that reaches 16 kilometers per second at the top of its trajectory will escape Earth's gravity entirely and enter heliocentric orbit around the Sun. Some of that material will eventually strike the Moon, some will be captured by Venus. Some will drift for millions of years before falling into something solid. The shock wave through the rock will reach you in approximately 4 minutes. You know it is coming. You feel the anticipation of it in the way the crust seems very slightly more alive beneath your feet. A faint, barely detectable trembling that may be real or may be the suggestion of it working through your imagination. Either way, you wait. The shock wave arrives. It comes up through the soles of your feet and moves through the length of your body in under a second, a rolling, low-frequency oscillation that begins deep in the crust and propagates upward. The ground does not crack dramatically. The motion is too slow for that, spread over too many kilometers of intervening crust. But a fracture line opens to your left, 2 centimeters wide, emitting a thin plume of steam from some subsurface water reservoir, heated past its boiling point. Steam. Water? You look at the plume for a long time. The water that is producing this steam did not come entirely from outgassing of the planet's interior. Some of it was delivered. In the early solar system, water was abundant in the outer regions. Locked in the ice of comets and asteroids, beyond the frost line, the distance from the sun at which water can remain frozen. As the late heavy bombardment flung objects inward, many of them were carbonaceous chondrites, a class of asteroid unusually rich in water-bearing minerals and organic compounds. When these objects struck the early Earth, the heat of impact released the water from its mineral bonds, and some fraction of it was incorporated into the planet rather than lost to space. Current estimates suggest that up to half of Earth's water budget may have been delivered by bombardment. The remaining half was outgassed from the interior, released by volcanic activity over billions of years, accumulated at the surface as the planet cooled. The ocean, in other words, came partly from the sky. The steam plume thins and disappears. The rock cools fractionally, closes partially over the fracture. To the north, the glow is still bright, but no longer growing. The ejecta plume is spreading through the upper atmosphere, and the light it scatters is diffusing the northern horizon into a deep orange band that will persist for days. You sit down on the warm basalt and you listen to the volcano in the east, and you watch the orange sky, and you understand that you are sitting in the middle of a process that has no single cause and no single effect, only a chain of events stretching back to the formation of the solar system and forward to every living thing that will ever exist on this planet. The bombardment is the context for everything. It shaped the moon, it delivered water, it sterilized the surface repeatedly, preventing any early chemistry from stabilizing prematurely, forcing life, when it eventually arose, to emerge in conditions robust enough to persist. Some scientists have argued that the bombardment was not merely compatible with the origin of life, but necessary for it, that the heat and chemistry of impact events created the precise conditions in which the first self-replicating molecules could form. That argument is not settled. But tonight, sitting on this warm basalt, watching the steam dissipate and the northern sky glow, you feel the logic of it. Something enormous is happening, and it is making something possible. The same force that is burning this world clean is seeding it with everything it will ever need. Above you, Jupiter and Saturn continue their slow gravitational conversation. The resonance is deepening. The sky above the shallow sea to the south shimmers with reflected light. And somewhere in the outer solar system, the next object has already begun its inward journey. You lean back against the rock. The rumble from the east continues. The sky is orange. You close your eyes. The ground is warm. You are 4 billion years from home, and somehow, this is where everything begins. This ancient surface holds you. The night, if this can be called a night, is very long, and there is more to come. The glow to the north has not faded. It has been 3 days since the impact, by the slow count of this planet's rotation, a day that currently lasts approximately 15 hours, not the 24 you are accustomed to. The early Earth rotated faster. The moon's tidal drag, operating over billions of years, would gradually slow that rotation to its current rate, but that braking has barely begun. The days here are short and violent, cycling quickly from the dull orange of atmospheric daylight to the fractionally cooler darkness of night. A darkness that is never truly dark because the northern horizon still pulses with residual thermal radiation from the impact site. You have not moved far, a few kilometers perhaps, along the ridge of a basaltic formation that gives you a slightly higher vantage point. Below you and to the west, the shallow sea you observed earlier has changed. The shock wave that passed through the rock 3 days ago also propagated through the water at a faster velocity, approximately 1.5 kilometers per second through liquid water compared to just over 5 kilometers per second through basalt. And when it reached the shallow basin, it displaced the water upward in a standing wave that crested at perhaps 15 meters and broke against the basin's far rim, surging across the surrounding rock and temporarily flooding several hundred square kilometers of surface before draining back. The water that returned was different from the water that had been there before. The impact had happened in basaltic crust to the north, and the ejecta plume had distributed pulverized rock, including minerals rich in iron, magnesium, and silica, across thousands of kilometers of atmosphere. Some of this material has now settled into the shallow sea as a thin layer of fine particulate, altering the water's chemistry. The water is rich in dissolved minerals already, heated from below by the geothermal gradient, and the addition of impact ejecta changes the balance of its chemistry in ways that are small but cumulative. Each impact leaves something behind. You sit on the ridge and watch the sea and think about chemistry. The early ocean, what scientists sometimes call the Hadean Ocean, from the Greek Hades, meaning the underworld, was not the vast, relatively stable body of water that covers 70% of the modern Earth. It was shallower, warmer, more chemically complex, and far less extensive. The continents, in the form we would recognize them, did not yet exist. The surface was dominated by oceanic crust, thin, dense basalt, with only the earliest, most primitive forms of continental crust beginning to accumulate in small, unstable islands. The total volume of water on the early Earth was likely similar to today, but without the deep ocean basins created by plate tectonics, it spread more broadly across the surface, forming a global shallow ocean punctuated by volcanic ridges and impact craters. That global shallow ocean was not continuous during the Late Heavy Bombardment. The largest impacts, those capable of delivering energy on the order of 10 to the power of 26 joules, were theoretically capable of vaporizing the entire surface ocean. The water would not have escaped to space entirely. It would have entered the atmosphere as steam, a dense, hot, high-pressure envelope surrounding the planet, and over thousands of years, as the surface cooled, it would have rained back down. This process, the vaporization and recondensation of the ocean, may have happened multiple times during the peak of the bombardment. You watch the sea and understand what you are looking at. This particular body of water may have been vaporized and reassembled within the last 10 million years. It may have been vaporized and reassembled several times. What looks like stillness, the slow shimmer of thermally active water under an orange sky, is actually the latest iteration of a cycle of destruction and reconstruction that has no human analog. Above you, the sky has changed again. The particulate matter from the northern impact is still spread through the upper atmosphere, but it is beginning to fall. The stratosphere acts as a temporary reservoir for fine particles, particles small enough that atmospheric drag slows their fall rate to centimeters per second. The settling time for particles of this size is measured in weeks or months. During that time, the particles scatter and absorb incoming solar radiation, reducing the amount of light reaching the surface. This is not insignificant. A reduction in solar radiation, even a partial one, changes the energy budget of the surface. Less energy in means lower temperatures, fractionally, temporarily, but measurably. The early Earth was already colder than its proximity to the sun might suggest. The young sun's lower luminosity, combined with a surface that had not yet accumulated the greenhouse gases that will eventually warm the planet, meant that without some additional warming mechanism, the surface should have been below freezing. It was not. The rock beneath you is warm, the sea beside you is liquid, and the reason is geothermal heat, the internal heat of the planet, supplemented by the constant energy input of the bombardment itself, kept the surface above freezing even when the young sun could not. This is the faint young sun paradox, first articulated by Carl Sagan and George Mullen in 1972, and it has no fully satisfying resolution even in the 21st century. The early Earth should have been a frozen ball of rock by the numbers. It was not. The bombardment may have been part of the answer. Impact heating, combined with a thick, reducing atmosphere and the internal thermal output of a young, radioactively hot planet, collectively kept the surface warm enough for liquid water to exist in places and at times that simple solar energy calculations would not predict. You think about paradoxes, about systems that should not work and do. The sea to the west is still there. A shape moves beneath its surface, a trick of light and refraction, a pattern in the thermally disturbed water that resolves as you look at it longer into the circular boundary of a hydrothermal vent. The water above the vent is slightly clearer, slightly more agitated, slightly warmer. The vent itself is a fracture in the seafloor, one of thousands created by the same impact shock waves that cracked the surface around you, through which superheated water circulates, carrying dissolved minerals from deep in the crust and depositing them at the vent opening as the pressure drops and the water cools. Hydrothermal vents. The significance of this observation will not be fully understood for another 4 billion years. But in the 21st century, scientists studying the origin of life on Earth will point to these vents, alkaline hydrothermal vents in particular, slightly different in chemistry from the high-temperature acidic vents discovered at oceanic ridges, as the most chemically plausible locations for the first self-replicating molecules to form. The steep gradient between the hot, mineral-rich vent water and the cooler, differently composed ocean water creates a natural proton gradient, a difference in hydrogen ion concentration across the thin mineral walls of the vent's internal pore structure. This gradient is essentially the same kind of gradient that drives ATP synthesis in the cells of every living organism on Earth today. The first chemistry that would eventually become life may have been powered by the same thermodynamic principle as the last. You watch the vent and you cannot know this, but you watch it anyway. The sky brightens again, not from the north this time, from directly above. This is different. You track the light with your eyes, a streak of white, moving fast, entering the atmosphere at a shallow angle from the east, and tracking west across the upper sky before the friction of the atmosphere slows it, heats it, and it brightens to a fireball, white hot, leaving a glowing trail of ionized gas and vaporized rock, stretching across the full visible arc of sky. It lasts approximately 40 seconds. Then the fireball itself dims. The object has either burned completely or survived to strike somewhere beyond the western horizon, and the glowing trail fades from white to orange to a reddish stripe that will persist for several minutes before diffusing into the general atmospheric haze. A bolide, a large meteor, not the kind capable of producing the basin-forming impacts that will define this geological epoch, but large enough to survive partial atmospheric entry and deliver significant material to the surface. The trail fades. Another follows it minutes later, smaller, dimmer, a brief streak across the upper sky, gone before you fully register it. Then two more in quick succession, moving along nearly identical trajectories, suggesting they are fragments of a larger object that broke apart in the outer solar system months or years ago and is now encountering the Earth as a dispersed cluster of related impactors. You watch the sky as an astronomer might, noting directions and angles and durations, not with scientific instruments, you have none, but with the careful attention that this moment demands. The bombardment is not a single drumbeat. It is a complex rhythm, basin-forming impacts separated by centuries or millennia, scattered against a continuous background of smaller strikes, bolides, airbursts, and the constant micrometeorite flux that has always rained down on the planet, even in geologically quiet times. The number of objects striking the early Earth each year during the peak of the Late Heavy Bombardment was orders of magnitude higher than today's rate. Today, the Earth gains approximately 40,000 tons of extraterrestrial material per year, mostly micrometeorites and dust. During the Late Heavy Bombardment, that number was vastly higher. The contribution of large impactors alone, objects more than 1 kilometer in diameter, may have been 100 to 1,000 times the current rate, depending on which model of the bombardment's peak intensity is correct. The Neukom production function, a mathematical model of the impact flux over time, gives estimates of approximately 1,000 impactors greater than 10 kilometers in diameter, striking the moon during the Late Heavy Bombardment. Earth, with a larger cross-section and stronger gravitational pull, would have received roughly 20 times that number, 20,000 large impactors in 300 million years, roughly one every 15,000 years. One every 15,000 years sounds infrequent, but each one was an event capable of devastating a continent. You look at the rock beneath your feet and understand that you are standing on a surface that has been hit by something capable of devastating a continent within the geologically recent past. Recently, in this context, meaning within the last few million years. The crater beneath you, the one your ridge is the eroded remnant of, was formed by an impactor that excavated a basin perhaps 300 kilometers across, deep enough that the rebound of the compressed crust beneath the impact point created a central peak of uplifted rock that has since been eroded by thermal cycling and later impacts into the low ridge where you now stand. Everything here is the remnant of something that was once the edge of a catastrophe. The moon above you is still large and bright. Even through the atmospheric haze, you can see its surface clearly enough to discern the darker regions, the mare, the ancient basins, from the brighter highlands. The highlands are the original lunar crust, the anorthosite formed when the moon itself was young and covered in a magma ocean, and the lighter rock floated to the surface as the magma cooled. The darker mare are younger, basaltic plains formed by volcanic flooding of the large impact basins. One of the largest of those basins, the South Pole Aitken Basin on the moon's far side, is over 2,500 kilometers in diameter and 8 kilometers deep. It is the largest confirmed impact crater in the solar system. The object that formed it struck the moon so hard that it punched through the crust and into the upper mantle. The impact scattered ejecta across the entire lunar surface. It may have occurred before the Late Heavy Bombardment, in the earlier period of heavy bombardment that preceded the lunar cataclysm, or it may have been among the first and largest impacts of the bombardment period itself. The exact timing remains under investigation. The moon keeps its secrets in the way that all geological bodies keep secrets, written in rock, readable only with instruments and methods that will not exist for another 4 billion years. You look at the moon and you know you are seeing a face that will still be visible from Earth in the 21st century, changed only slightly by the slower impact rate of the subsequent eons, recognizable to anyone who has ever looked up on a clear night and traced the dark patterns of the mare with their eyes. The same face, different craters forming on it tonight. A sound reaches you from below, from the sea to the west, a deep rhythmic thudding, regular as a pulse, that you realize after a moment is not geological in origin. It is the collision of waves against the rim of the basin, the tide, driven by the enormous gravitational influence of the close moon, surging against the edges of the shallow sea every few hours, rising and falling by tens of meters with each cycle. The tidal forces at work during this period of Earth's history were not just affecting the water, they were affecting the crust. The solid Earth tides, the deformation of the rocky crust itself under the moon's gravitational pull, were larger and more energetically significant than they are today. The crust flexed and recovered with each tidal cycle, generating friction heat deep in the interior and providing an additional heat source to supplement the radioactive decay and residual accretionary heat. Every piece of this system was warming itself, every process feeding into every other. Radioactive decay heated the mantle, which heated the crust. Impact bombardment added energy from above, while tidal flexing sent additional heat into the deep interior. The geothermal vents released that heat into the water, and the water vapor rising into the atmosphere trapped it there, against the cool of space. The planet was running hot. And in that heat, in the specific chemistry of a world that was too warm, too geologically active, too constantly bombarded to settle into a stable frozen equilibrium, something was beginning to organize. Not life, not yet, but the conditions that would eventually permit life. The distinction matters. Life does not spring into being at the first available opportunity. It requires not just the right chemistry, but the right conditions for that chemistry to persist long enough to become self-sustaining. On Earth, the gap between the formation of the planet and the earliest confirmed fossil evidence of life is approximately 800 million years, from 4.5 billion years ago to approximately 3.7 billion years ago, when stromatolites, layered microbial mats produced by communities of photosynthetic bacteria, appear in the rock record of the Isua Greenstone Belt in Greenland and the Dresser Formation in Western Australia. 800 million years of chemistry. You are in the middle of that 800 million years. The bombardment is part of it. You stand up and look east, where the volcano continues its slow, enormous exhale. The gases rising from the vent, carbon dioxide, sulfur dioxide, water vapor, nitrogen, trace amounts of hydrogen and methane, are not just pollution, they are atmosphere. Every molecule of gas released by volcanic activity during this period is adding to the growing atmospheric inventory of a planet that arrived relatively gas-poor and is building its atmospheric density from the inside out. The gases rising from the volcanic vent are not byproducts of geology. They are the raw material of an atmosphere. Water vapor, carbon dioxide, sulfur dioxide, nitrogen, every molecule exhaled by the interior is adding to the growing atmospheric inventory of a planet assembling itself from the inside out. The rate will slow over billions of years as the interior cools, but it will never fully stop. A planet building its own sky. The thought stops you for a moment. A planet building its own sky and simultaneously being seeded with the raw materials of chemistry, water locked in ice, carbon and rock, nitrogen and gas, all of it operating on timescales that make the entirety of human history look like a single heartbeat. The Baladay Trail from earlier has long since faded. The sea to the west is quiet in its restless way. The northern glow has dimmed to a barely perceptible warmth on the horizon. And above the moon, above the haze, above the full depth of this dense building atmosphere, another object has begun its descent. You cannot see it yet, but you feel in the quality of this moment that the sky is preparing something. The tides surge against the basin rim below you. The volcano exhales. The moon watches. Every impact that has fallen on this world has left something behind, not just a crater, a change in chemistry, a shift in temperature, a new compound in the water. Every collision was also a delivery. You watch the sky. You are standing in the chapter of Earth's history that will make everything else possible. And the next impact is already entering the upper atmosphere. You can see the glow beginning. You stay where you are. The rock beneath your feet is warm. The sky is orange and alive. And you are exactly where you are supposed to be. The shallow sea is gone. You know this not because you watched it disappear, but because the ground where it stood is now the same temperature as everything else, above 200 degrees at the surface, higher below. The thin mineral crust that had formed over the cooled water now fractured and reabsorbed into the surrounding basalt, as if the sea had never existed. It was vaporized, not by an impact nearby, by one far enough away that the shock wave through the rock was barely perceptible, a soft tremor, easily mistaken for the background geological noise of a planet that never stops moving. But the thermal energy released by that distant impact was sufficient to raise the atmospheric temperature by several degrees over the course of a week, and a sea only a few meters deep, already close to its boiling point, does not survive a week of additional atmospheric heating. The water is in the sky now. You can feel it, a density in the air, a pressure slightly greater than before, the humidity of a steam bath multiplied beyond any human reference point. The water vapor in the atmosphere above you represents the entire contents of that shallow basin, suspended, waiting for the conditions that will allow it to fall again. Those conditions will return. They always return. But not tonight. Tonight the atmosphere is loaded with water vapor and particulate matter from a dozen recent impacts, and the sky has taken on a texture you have not seen before. Not the smooth amber haze of the baseline atmosphere, but something layered, streaked with darker bands where convection currents are moving the warm, moist air upward in columns that flatten against the upper thermal boundary and spread sideways, forming a canopy of cloud-like structures that are not quite clouds, not in the way clouds will exist in 4 billion years. They are the first approximation of clouds. They are the early Earth learning how weather works. You watch them move. The convective cells are enormous, each one spanning hundreds of kilometers, driven by the temperature differential between the surface and the upper atmosphere. Warm, humid air rises from the surface, cools as it climbs, releases its water vapor as fine droplets of acid-laced condensation, and then descends again at the edges of the cell. The cells are organized. They have structure. They are, in the most primitive sense, the beginning of the atmospheric circulation patterns that will one day drive the global climate system. The first suggestion of wind moves past you, not the gentle, salt-tinged breeze of a modern coastline, but a hot, chemical-laden gust carrying sulfur dioxide from the volcanic province to the east, and fine particulate from the most recent impact ejecta to the north. You lean into it slightly. It is not comfortable, but it is real. Below you, kilometers below you, in the deep interior of a planet still running far hotter than it will in any future era, something is building. The magma ocean. The term is not metaphorical. In the first 100 million years of Earth's existence, the entire planet was molten, a sphere of liquid rock, cooling from the outside in, crystallizing slowly as heat radiated away into space. By the time the Late Heavy Bombardment began, most of that original magma ocean had solidified. A thin crust had formed, a mantle had differentiated, a core had separated. But the bombardment remelted it. Not all of it, and not all at once. The largest impacts, the basin-forming events capable of releasing energy equivalent to millions of nuclear weapons, delivered enough thermal energy to locally melt the crust and upper mantle over areas hundreds of kilometers across. In regions of particularly intense bombardment, where impacts occurred in close succession without time for cooling, the cumulative effect was the formation of localized magma lakes, pools of molten rock at the surface, sometimes hundreds of meters deep, sometimes connected by channels of flowing lava to broader magma provinces deeper in the crust. You are standing near the edge of one of these provinces. The ground to your left, 100 meters away, no more, ends at a boundary that you identified by the heat radiating from it before you saw it. The rock beyond that boundary is not solid. It is a dark, glossy surface that shifts slowly, almost imperceptibly, as the convective currents in the liquid rock below it move against the underside of the thin, solidified skin. The skin is perhaps 10 centimeters thick. It breaks periodically, a crack opening, a bright orange line of liquid rock appearing briefly, then cooling and sealing again as the surface skin reforms. The temperature at the edge of this magma pool is approximately 1200 degrees Celsius. You do not approach it. You watch from the cooler margin where solid ground meets the fractured transition zone, and you observe a process that will not be reproduced on the surface of the Earth again for geological ages, not until future geologists study young volcanic systems like Iceland and Hawaii and piece together from those much smaller analogs what this surface once looked like. The magma is not silent. It produces a low, continuous sound, a deep, resonant hiss generated by the outgassing of dissolved volatiles. As the pressure drops at the surface and gas bubbles escape from the liquid rock, carbon dioxide, sulfur dioxide, water vapor, hydrogen sulfide, each bubble that bursts at the surface of the magma lake releases a small package of these gases into the atmosphere above, adding fractionally to the atmospheric pressure, fractionally to the greenhouse gas concentration, fractionally to the chemical complexity of the air. This is how the atmosphere was built, one bubble at a time. The process you are watching right now at this single magma pool on the edge of a scarred continent is happening simultaneously across thousands of vents, across every ocean basin, across every volcanic province on the planet. Each is exhaling into the same sky. Each is adding its fraction to the same accumulating atmosphere. This is the factory, and it never closes. You sit down at the safe margin and watch the surface of the magma shift and crack and heal and shift again, and you think about scale. The magma pool in front of you is perhaps 50 kilometers across, enormous by any human measure, but insignificant compared to the magma provinces forming simultaneously in the deep ocean basins thousands of kilometers away, where the crust is thinner and the impacts have been more numerous, and the thermal input from the interior is higher. In those regions, the magma ocean is not a pool. It is an ocean in the literal sense, a continuous body of liquid rock covering hundreds of thousands of square kilometers, deep enough in places that the pressure at the bottom begins to suppress the same volatile outgassing that characterizes the shallower pools. The ocean floor is being continuously resurfaced by this magmatic activity. The thin oceanic crust that formed between bombardment events is being remelted and replaced with fresh basalt, losing whatever record it might have contained of conditions at the time of its formation. This is why so little direct evidence of the Hadean survives. The crust was reprocessed, recycled, remelted. The evidence of the first 500 million years of Earth's history was destroyed not by carelessness, but by the energetic thoroughness of a planet still learning how to cool itself. The few fragments that survive, the Jack Hill zircon crystals, locked inside later conglomerate rock in what will one day be Western Australia, survive precisely because they were small enough, hard enough, and chemically stable enough to resist the reprocessing that destroyed everything around them. Within each crystal, atoms of uranium were locked into the mineral lattice at the moment of crystallization. Uranium decays to lead at a fixed and measurable rate, uranium-238, with a half-life of 4.468 billion years. By reading the ratio of uranium to lead trapped inside a single crystal, A geochemist 4 billion years from now can calculate the age of its formation to within a few million years. The crystal closing around its first uranium atom right now is starting a clock. It will not be red for 4 billion years, but it will be red. The oldest material on Earth is not a mountain. It is a crystal smaller than your fingernail. It has been running a clock since the moment it formed, and it has not missed a single second. The magma pool shifts again. A new crack opens, longer this time, running for perhaps 20 meters before the pressure equalizes and the crack seals. Through that brief opening, the interior of the pool is briefly visible, not the dark, glossy surface skin, but the fully liquid rock beneath it, white-orange with heat, moving in slow, viscous waves driven by the convective currents far below. You watch it seal. The chemistry happening in that magma is not simple. Magma is not a single substance. It is a complex silicate melt containing dissolved gases, trace metals, radioactive isotopes, and a range of mineral compounds that will crystallize in a specific sequence as the melt cools. The process of fractional crystallization, the selective crystallization of different minerals at different temperatures as the magma cools, is what produces the diversity of igneous rock types found in the geological record. The first minerals to crystallize from a cooling crustic magma are olivine and pyroxene, forming at temperatures above 1000 degrees. As the temperature drops, plagioclase feldspar begins to crystallize. Lower still, and more exotic mineral assemblages appear, minerals that will not survive to the modern era in recognizable form, but whose chemical signatures will be preserved in the zircon crystals and in the isotopic ratios of ancient rock formations that future geologists will analyze with instruments of extraordinary precision. Every mineral that crystallizes from this magma is a record, a timestamp, a piece of evidence in an investigation that will not begin for 4 billion years. The heat from the pool radiates against your face, not uncomfortably in this imagined presence, but perceptibly. You are aware of it as a physical fact. The surface of the Earth is hot, not metaphorically, not in some geological abstraction, hot in the immediate physical sense, hot in the way that things that are on fire are hot. The planet is on fire, and inside that fire, chemistry is happening. The organic chemistry of the early Earth is one of the most actively debated areas of modern science. The question is not whether complex organic molecules existed in the early Earth environment. They did, delivered by carbonaceous chondrites, and formed in the atmosphere by lightning discharges through the reducing gas mixture. But whether those molecules could survive long enough and in sufficient concentration to participate in the reactions that eventually produced self-replicating chemistry. The Miller-Urey experiment of 1953 demonstrated that amino acids, the building blocks of proteins, form spontaneously when an electrical discharge passes through a mixture of methane, ammonia, water vapor, and hydrogen. The atmosphere of the early Earth was not identical to the mixture used by Miller and Urey, but it contained the same essential components, and lightning was abundant. Lightning was more than abundant. The early Earth's atmosphere, loaded with charged particulate from constant volcanism and impact events, was electrically active at a level that would be considered catastrophic by any modern standard. Lightning discharges occurred continuously across the full extent of the atmosphere, producing organic molecules in the gas phase and delivering them to the surface with every rainstorm, every event where the water vapor in the atmosphere finally cooled enough to condense and fall. The rain that fell on the early Earth was not clean. It was a dilute chemical soup. A warm rain falling onto a warm sea, carrying organic molecules synthesized in the atmosphere, mixing with minerals dissolved from the basaltic crust, pooling in hydrothermal vent systems where temperature gradients and mineral surfaces provided the catalytic conditions for further chemical reactions. This is the broth. Not a simple broth, not a static one, a broth constantly being stirred by tidal forces, heated and cooled by hydrothermal activity, irradiated by ultraviolet light from a young sun with no ozone layer to filter it, seeded by each new impact with fresh chemical inputs, and disrupted by each shock wave passing through the rock below. The conditions were violent. They were also, in a specific and important sense, creative. The magma pool in front of you has been quiet for several minutes, relatively quiet, its surface intact, the cracking and resealing paused as the convective currents beneath it shift into a new configuration. The glow from its surface is the dominant light source in your immediate environment, casting everything in a shifting orange-red that has its own strange beauty. You look at that light and you understand something about this moment. This is not the end of the world. This is the beginning of it. The bombardment that is destroying every surface feature, vaporizing every nascent ocean, melting every newly formed crust. It is also mixing. It is also delivering. It is also heating the environments where chemistry happens and sealing them under new layers of rock when they grow too complex, and excavating them again with the next impact and redistributing their contents across the surface of the planet. The Late Heavy Bombardment was the greatest mixing event in Earth's history. It was the planet turning itself inside out. It was a 4-billion-year-old laboratory running an experiment without a scientist, without a hypothesis, without an expected outcome. And yet, from that chaotic, burning, acid rain-soaked, lightning-scarred, magma-pooled surface, something will emerge. Not tonight, but the chemistry is already beginning. Under the light of a magma pool, on a planet that should not be able to support anything, the first molecules that will one day become you are forming in the rain. The crack in the magma surface opens again. Orange light floods the margin where you sit. Then it seals. Then it opens again. The rhythm of it is almost like breathing. The planet inhales. The planet exhales. And the chemistry continues. The rhythm continues for a long time. You watch the magma pool in its slow, almost meditative cycle of cracking and sealing, and you begin to understand that what you are witnessing is not chaos, or not only chaos, there is structure within it. The fracture lines that open in the surface skin of the pool follow the same paths repeatedly. The convective cells in the liquid rock below move in patterns that are not random, but governed by the same fluid dynamics equations that will one day describe the behavior of water in a heated pot, the behavior of the atmosphere in a storm, the behavior of the outer core generating the magnetic field that protects everything above it. Physics does not change. The same equations that govern this burning surface govern the formation of the first galaxies, and they will govern the movement of air over the wings of birds that have not yet evolved, and they are governing right now the slow drift of the planet you are standing on through its orbit around a young star. Everything is connected by physics. Everything has always been connected by physics. The thought is not comforting in a soft way. It is comforting in a harder, more durable way. The way that understanding something real about the structure of the universe is comforting, not because it makes things easier, but because it makes things coherent. You're not in chaos. You are in the early stages of a very long order. The temperature on the surface around you has dropped by approximately 8 degrees over the course of the last several hours. Not dramatically. The surface is still far above any temperature that would feel comfortable or survivable by biological standards, but 8 degrees is measurable. 8 degrees over 4 hours, repeated consistently, represents a heat flow rate, and a heat flow rate maintained over geological time represents cooling. The planet is cooling, imperceptibly slowly by human standards, but measurably by the standards of the instruments that will one day be brought to bear on the ancient rock record. Every mineral that crystallizes from a cooling magma carries within its atomic structure a record of the temperature at which it formed. The ratio of certain isotopes locked into crystal lattices at the moment of crystallization, what geochemists call a geothermal barometer, can be read by a mass spectrometer 4 billion years later and used to reconstruct the temperature conditions of the early Earth with remarkable precision. The crust is keeping records even as it forms. Every crystal that closes around a trapped atom is writing a date, a temperature, a composition into the archive. You are watching 4 billion years of evidence being written in real time. 40 kilometers to your east, the volcanic province that has been exhaling since you arrived is doing something new. The eruption pattern has shifted, not ended, but changed in character. The low, continuous rumble that has been the baseline sound of your environment has acquired a new overtone, a higher frequency pulse, rhythmic, spaced perhaps 30 seconds apart, that represents a change in the eruptive style from the slow effusion of fluid lava to the more energetic emission of volcanic gases under higher pressure. This is a sign of change in the magma supply system below. The magma chamber feeding this volcanic province, a body of partially molten rock perhaps 20 kilometers in diameter, sitting at a depth of 15 to 20 kilometers in the crust, is being recharged from below. Fresh mantle material, driven upward by the convective forces in the deep interior, is adding new heat and new gases to the chamber. The increased gas content raises the pressure. The pressure finds release in the new eruptive rhythm. The planet is not winding down. It is cycling. Input and output, heat in, heat out, material rising, material sinking, gas released, gas captured, water vaporized, water condensed and fallen and vaporized again. The early Earth is not a linear system trending towards some final state. It is a complex, nonlinear system, finding new equilibria, losing them, finding others. The bombardment adds energy to this system. Each impact is a perturbation, a sudden injection of thermal and kinetic energy that pushes the system away from whatever equilibrium it has most recently reached and forces it to find a new one. The surface melts, the atmosphere heats, the water vaporizes, and then, over thousands of years, the system cools again, the water returns, the new crust forms, and a new equilibrium is established, until the next large impact. The resilience of this system is extraordinary. Not the resilience of something strong enough to resist disruption, the resilience of something flexible enough to absorb disruption and reorganize around it. The early Earth is not surviving the bombardment, it is being shaped by it. And what it is being shaped into, slowly, over the course of 300 million years, is a world. The magma pool to your left has gone quiet again. Its surface is fully sealed now, a smooth, dark expanse broken only by the faint shimmer of radiated heat above it. The glow that illuminated the surrounding crust earlier has faded to a dull copper red. You stand up. The sky above you is different from the sky you looked at in the first hours of this journey. The convective cloud structures that formed earlier in the day have developed further. They are taller now, reaching higher into the atmosphere, their upper portions spreading into thin, elongated shapes where the temperature is cold enough for the water vapor to condense into actual ice crystals. Not clouds in the modern sense, but something that functions like clouds, something that intercepts solar radiation, reflects some of it back to space, allows some of it through. The early Earth is learning to regulate its own temperature. Not through intelligence, not through design, through the blind, iterative logic of physical and chemical systems, finding the conditions that allow them to persist. Everything this planet will become is already being decided right now, in the chemistry of cooling rock, in the physics of moving gas, in the slow, patient logic of a system that does not know it is building a world and is building one anyway. The volcanic pulse to the east settles back into its steady rhythm. The magma pool rests. The sky above you carries its first real clouds, high and thin and fragile, but present. You sit back down and look up at the clouds, the thin, high structures that were not there yesterday, that the atmosphere has assembled from water vapor and particulate and the slow logic of convection. They are fragile. They are real. The planet is learning something new about itself, and the chemistry in the magma and the air and the rain that has not yet fallen continues. The impacts are becoming less frequent. You notice this not as a relief, not as a release of tension, but as a change in the texture of time itself. In the early hours of this journey, there was always something arriving, a glow on one horizon or another, a tremor in the rock, a new streak across the sky. The bombardment was continuous in the way that heavy rain is continuous, individual drops impossible to distinguish from one another, the overall effect an unbroken density. Now there are gaps. The gaps are not long, measured against human time, a week without a major impact, 2 weeks, a month of relative quiet in which the volcanic activity continues, the atmosphere churns, the magma province to your left slowly seals itself more completely, but the sky does not brighten with new arrivals, and the ground does not shudder with new shockwaves. And for the first time since you arrived in this era, you can hear something other than the constant percussion of the bombardment. You can hear the planet itself. The deep, slow respiration of a world exhaling through 10,000 volcanic vents simultaneously. The hiss of water vapor releasing from the rock. The subsonic rumble of mantle convection felt in the soles of your feet more than heard. A vibration so low in frequency that it exists below the threshold of hearing and registers instead as a physical pressure. The planet is not quiet. It will never be entirely quiet, not for the rest of its existence, but the quality of the noise has changed. The violent, percussive chaos of the peak bombardment is giving way to something more rhythmic, more geological, more, in some hard-won sense, stable. This is what the end of a geological catastrophe sounds like. Not silence, not peace, just a slightly lower rate of destruction. The date, by the best estimates of scientists who will piece this together 4 billion years from now, from the isotopic ratios in ancient lunar rocks and terrestrial zircon crystals, is approximately 3.9 billion years before the present. The late heavy bombardment is not over. It will continue at a declining rate for another 100 million years, but the peak intensity has passed. The most unstable orbits have been cleared. The largest reservoir of potential impactors has been depleted. The solar system is settling, not into the configuration it has today. That final arrangement is still billions of years away, but into something more stable than what preceded it. The orbits of Jupiter and Saturn, having passed through their resonance, have moved past it and begun to diverge again, reducing the gravitational pumping that drove the bombardment. The flux of large impactors falling toward the inner solar system is declining exponentially, following the same mathematical curve that characterizes any depleting reservoir. You look up at the sky. The clouds that formed in the last period, the thin, high structures that were the early Earth's first attempt at weather, have developed. They are lower now, denser, organized into bands that circle the globe along the thermal gradients between the equatorial regions and the poles. The equatorial atmosphere is warmer, driving upward convection. The polar regions, still far too warm for any ice to persist at any latitude, are measurably cooler, pulling the upper atmosphere air poleward and creating the first approximation of atmospheric circulation cells. The Hadley cells are forming. Named 4 billion years from now after George Hadley, an 18th century English meteorologist who first described the mechanism, but operating here now for the first time as the early Earth's thermal gradient drives the first organized circulation of its atmosphere. Warm air rises at the equator, moves poleward at altitude, cools, descends, and returns equatorward near the surface. The descending air compresses and warms slightly, creating bands of relatively drier conditions. The rising equatorial air cools and drops its moisture. The planet is learning to rain. Below you, the geological activity that has defined every moment of this journey is continuing, but at a changed pace. The magma pool to your left has been fully sealed for 3 days now. The crust over it is thicker than it was, perhaps 20 centimeters, compared to the 10 centimeters of a week ago. The fractures are healing. The fresh volcanic material that cooled from the surface of the pool has begun to accumulate a thin layer of chemical alteration products, iron oxides, hydrated silicates, the earliest minerals that form when fresh basalt is exposed to the chemically reactive early atmosphere. The rock is being weathered. Chemical weathering of silicate rocks, the process by which rain and atmospheric gases react with exposed rock surfaces, breaking down the mineral structure and releasing ions into solution, is one of the most important geochemical cycles on Earth. It removes carbon dioxide from the atmosphere, locking it into carbonate minerals that eventually end up on the ocean floor. It releases calcium, magnesium, potassium, and phosphorus, nutrients that will one day be essential to all living things, into the water that flows across the surface. On the early Earth, with no land plants to protect the soil and no thick soil to slow the reaction, the rate of silicate weathering was enormously high. Bare mineral surface exposed to a dense carbon dioxide-rich atmosphere and slightly acidic rain reacted rapidly with exposed mineral surfaces. The early ocean was saturated with dissolved minerals in concentrations far higher than the modern ocean. The water, if you could stand in it, would not look like modern seawater. It would be murky, mineral-rich, and chemically complex, rich in dissolved iron, silica, sulfur compounds, and a range of organic molecules synthesized in the atmosphere and delivered by rain and by impacting carbonaceous asteroids. It would not taste like anything you have ever tasted. It would taste like the beginning of everything. A drop falls on the rock beside you. Then another. Rain. Not the first rain that has fallen on this planet. There has been rain intermittently since early in the Hadean, falling briefly during cooling episodes between impact events and rapidly re-evaporating as the surface heat reasserted itself. But this rain feels different. The drops are larger. The intervals between them are shorter. The rock beneath them darkens where they fall, staying dark instead of immediately flashing to steam. The surface is cool enough to hold water. You hold out your hand in imagination, in the full reality of this imagined presence, and a drop falls into your palm. It is warm. It carries the chemistry of the atmosphere through which it fell, slightly acidic from dissolved carbon dioxide, faintly sulfurous, carrying traces of iron oxide and fine silicate dust from the impact ejecta, still settling from the stratosphere. It is not clean water. It is the most chemically rich water that has ever fallen on any surface anywhere in the solar system. It sits in your palm for 3 full seconds before evaporating. 3 seconds. Impossibly brief by the standards of what is coming, the day 400 million years from now, when water will pool and persist and deepen and eventually cover 70% of this planet's surface and remain there for the rest of geological time. But 3 seconds is longer than before. 3 seconds is progress. You close your hand. The rain intensifies. What is happening above you is the beginning of a feedback process that will ultimately stabilize the climate of the early Earth and allow liquid water to persist at the surface. The mechanism is called the carbonate-silicate cycle, and it operates over millions of years as a thermostat, a natural regulatory system that prevents the planet from either freezing completely or heating past the point where water can exist as a liquid. The mechanism works as a thermostat. When the surface is warm, silicate weathering accelerates, consuming carbon dioxide and reducing the greenhouse effect. As the greenhouse thins, the planet cools and the weathering slows, allowing volcanic carbon dioxide to rebuild. The system oscillates around a stable point, neither heating nor cooling indefinitely. It has failed before. In Earth's future, global glaciation events, snowball Earth episodes, will overwhelm it temporarily. But across most of geological time, this cycle will keep the surface within the narrow temperature band where liquid water persists. It is beginning to operate right now. The carbon dioxide concentration of the atmosphere above you is somewhere between 10 and 40%, far higher than any modern value, far higher than the concentration that drives the climate concerns of the 21st century. The temperature at the surface is too high for ice to form at any latitude, but the weathering is happening. The rain is falling on fresh basalt and reacting with it, consuming carbon dioxide molecule by molecule, building toward the slow reduction in atmospheric concentration that will, over the next several 100 million years, allow the planet to cool toward temperatures compatible with life. The rain is doing what rain will do for the next 4 billion years. It is changing the world, one drop at a time. You are sitting in it now, in the chemically active rain of the early Archean, and the rock beneath you is darkening with moisture, and the sealed volcanic margin to your left is being filmed with a thin skin of water that immediately reacts with the hot basalt surface and produces a hiss of steam where liquid and hot solid meet. The planet hisses. The planet is learning to be wet. Above the rain, above the low clouds, above the Hadley circulation and the convective towers and the stratospheric layer of impact ejecta, still slowly settling after 100 million years of continuous bombardment, the moon is there, still large, still close, still pulling the tides that slosh the shallow seas and flex the crust with each passage. The moon is slightly farther away than it was when you first arrived. Not by much, a few hundred kilometers perhaps, in the time you have been here. The moon moves away from the Earth at approximately 3.8 centimeters per year, driven by tidal friction, the same mechanism that is slowing the Earth's rotation and transferring angular momentum outward to the moon's orbit. The process is imperceptible on any human timescale. But over the 4 billion years between now and the 21st century, it adds up to 344,000 kilometers of additional distance. The moon you grew up with, the moon that hangs in the night sky and drives the tides of the modern ocean, does not exist yet. It is still too close, still too large, still too gravitationally dominant. But it is already moving away. Everything here is in the process of becoming something else. The planet is cooling toward habitability. The atmosphere is thickening toward breathability. Not yet, not for billions of years, but the first steps of that chemical journey are being taken right now in the rain and the volcanic outgassing and the ultraviolet-driven chemistry of the upper atmosphere. The bombardment is declining toward the background rate that will persist at low intensity for the rest of the solar system's existence, a rate that is still, by the standards of the modern era, moderately active, but that represents the end of the catastrophic phase and the beginning of the merely geological. You sit in the rain and you feel the warmth of the rock through the thin film of water that has now accumulated on its surface. The water is 1 millimeter deep, then 2 millimeters. Then it begins to move, finding the lowest point, flowing slowly along the surface gradient, seeking the depression behind the sealed magma pool, where the rock dips slightly, forming the first puddle. A puddle? On a planet that was entirely molten within living geological memory. A puddle, 2 millimeters deep and perhaps 3 meters across, sitting in a depression in cooling basalt, under a warm rain, on a world that will one day hold oceans. You watch the water move. You watch the puddle grow. The same water that is pooling here in this small depression in ancient rock has been on this planet for billions of years. Some of it is in the ocean right now. Some of it is in you. The rain falls. The puddle deepens. The magma pool hisses and steams where the water reaches its edge. And somewhere in the chemistry of that boundary, where liquid water meets cooling volcanic rock under a sky full of lightning and organic molecules and the settling dust of 100 million impacts, something is becoming possible that was not possible before. The cooling is slow. It will take another 400 million years for the surface to cool enough that life can gain a permanent foothold. But the direction is set. The cooling has begun. The rain continues to fall. The water continues to move. The planet continues to breathe. And you sit in the middle of all of it, in the slow rain of the early Archean, on a surface that was molten not long ago, listening to the planet learn how to be itself. The sound of the volcanic province to the east has changed again, lower now, longer between pulses, settling into a rhythm that feels less urgent than before. The sky is lighter than it was. The clouds are real. The puddle beside you is 4 millimeters deep. You rest your hand on the wet rock. It is warm. It is cooling. And that is everything. Somewhere on this planet, in a region where the cooling rate and the magmatic chemistry are combining in exactly the right proportion, zircon crystals are forming. Their clocks are already running. Their uranium atoms are already decaying toward lead, one half-life at a time, patient and unstoppable. Each crystal forming in this rain-soaked, slowly stabilizing geological era is a message placed in a bottle. The bottle will survive everything: subduction, metamorphism, acid, pressure, and the message will still be readable when someone, 4 billion years from now, finally opens it. The rain outside is heavier now. The puddle beside you has grown. It is perhaps 10 meters across now, its surface dimpled by falling drops, its edges slowly encroaching on the fractured ground that slopes down toward the sealed magma pool. Where the water reaches the still warm rock at the edge of the pool, it steams. The contact zone between the advancing water and the residual heat of the magma province is a hissing, steaming boundary that shifts as the water advances and the rock cools. The water is winning. Not dramatically, not quickly, but measurably, in the way that cooling always wins eventually against heat when the heat source is declining. The bombardment that has been the primary heat source for the surface, supplementing the internal heat of the planet with the kinetic energy of constant impactors, is delivering less and less energy as the flux of objects declines. The surface heat budget is shifting, input is declining, output, through radiation into space, continues unchanged. The planet tips toward cooling. And with cooling comes change. The first sign of that change is already visible in the rocks forming in the rain. The chemical alteration products, the iron oxides and hydrated silicates, and clay precursors forming on the surface of the wet basalt, represent a new kind of rock, not the igneous rock produced by cooling magma, not the metamorphic rock produced by heat and pressure. Something in between, a transitional material, the earliest sedimentary precursor, the first indication that the surface of the Earth is not just being formed and reformed by volcanic and impact processes, but is beginning to be chemically transformed by the interaction of rock and water and atmosphere. Sedimentary rock, the rock that will eventually preserve the fossils of every creature that has ever lived, the rock that will record the chemical signature of every ocean and every atmosphere through the rest of geological time, begins here. In the chemical alteration of basalt by slightly acidic, mineral-laden rain, in the formation of clay minerals in the contact zone between fresh rock and moving water, in the pooled water beside you. The first sediment is forming in the water. Fine particles of chemically altered basalt, suspended in the water column, slowly settling to the bottom of the puddle as the current slows. They are a fraction of a millimeter in diameter. Their surfaces are reactive, coated in iron hydroxides and clay minerals that will, under the right conditions, interact with organic molecules dissolved in the water and potentially concentrate them, organize them, provide the surface chemistry that some scientists believe was essential to the origin of life. The surface of a clay mineral is a two-dimensional chemistry laboratory. The charges distributed across it attract and orient organic molecules, the same molecules that float randomly in solution, too dilute to interact productively with one another, can be brought into close proximity on a clay surface. Reactions that would take millions of years in solution can happen in thousands of years on a mineral surface. The puddle is small, but it is a beginning. You sit beside it and watch the sediments settle and the rain fall and the boundary between rainwater and hot basalt steam and hiss its slow retreat, and you feel not comfort exactly, but something in the direction of recognition. This is how it starts. Not with a single event, not with a moment of creation, with a puddle, with rain, with the patient, accumulative logic of molecular interaction operating over geological time, in a system that is slowly, imperceptibly, cooling toward the conditions where something more complex than chemistry becomes possible. The moon above is pulling the water in the puddle toward it, by an amount too small to measure without instruments, but real. The tidal force acts on every body of water at every scale on this planet. The ocean basins feel it most dramatically, but even this puddle, 3 meters across and 4 millimeters deep, is responding to the gravitational pull of a moon 35,000 kilometers above it. Everything is connected to everything. The atmospheric pressure above you is approximately 2 times the modern sea level pressure, denser than today, the weight of a thicker air column pressing down on the water surface of the puddle, the rock, your imagined presence here in this moment. You feel that weight? It is real. The weight of the ancient atmosphere pressing down on the first puddle of water on a cooling world. The same water that will fill oceans. The same water that will carry the first cells across the surface of the planet. The same water that is in every living thing that has ever existed on this earth. It is right here. It is 4 millimeters deep and 3 meters across. And it is the most significant body of water in the history of the solar system. The rain slows. The drops space out, further apart, lighter, the rainfall transitioning from the heavy convective downpour of an hour ago to a gentle, persistent drizzle as the convective cell above you reorganizes and the heaviest precipitation moves eastward toward the volcanic province. The puddle holds. The steam at the edge of the magma province fades to a thin veil. The sky is still orange. It will be orange for another billion years until the oxygen revolution changes its chemistry, but it is a lighter orange than before. The stratospheric haze is thinning. The impact ejecta is settling. The sunlight filtering through the atmosphere is reaching the surface with slightly less obstruction than it did in the peak years of the bombardment. The world is opening up to its own sun, fractionally, over millions of years. But the direction is clear. You lean back on the wet stone and you look at the sky and you feel the rain on your face, imagined, real, both at once, and you understand that you are sitting at the hinge point of a 4 billion year story. Behind you, the catastrophe. Ahead, everything else. The puddle is 6 millimeters deep now. The first sediment layer is 2 particle diameters thick. The zircon crystal forming somewhere over the horizon has closed around its first uranium atoms. The clock is running. The cooling has begun. And somewhere in the chemistry of this wet, mineral-rich, organically seeded world, the conditions for something unprecedented in the known universe are almost in place. Not tonight, but soon. In geological terms, soon. 400 million years have passed. You know this not because you lived through them. No single consciousness could, but because the world around you has changed in ways that only 400 million years of accumulated process can produce. The sky is still orange, but it is a lighter orange. The carbon dioxide concentration in the atmosphere has fallen, not to breathable levels, not yet, not for hundreds of millions of years more, but measurably, driven by the slow action of the carbonate-silicate cycle you watched beginning in the reign of the early Archean. The stratospheric haze that defined every sky you observed during the bombardment has settled. The impact ejecta is gone, incorporated into the geological record, layer by thin layer, a stratigraphic signature that future geologists will call the Late Heavy Bombardment boundary. The bombardment is over. Not the last impact. There will be impacts at a low and declining rate for the rest of the solar system's existence. A random asteroid will still find Earth's gravity occasionally, will still leave craters, will still change things. 66 million years from now, one such impact will end the reign of the non-avian dinosaurs, but the systemic catastrophic episode, the 300 million year period during which the flux of large impactors was elevated by a factor of 1,000, has ended. The solar system has found its current geometry, and the Earth that remains is unrecognizable from the world you first stepped onto. The surface temperature at your feet is approximately 70 degrees Celsius, still too hot for any human, still well above the boiling point of water at low pressure, but cold by the standards of the Hadean surface you first stood on. The rock beneath you is a different kind of rock. Not fresh, hot basalt erupted from the mantle yesterday. Ancient rock, metamorphosed by heat and pressure over hundreds of millions of years, folded and refolded by the tectonic stresses of a crust, finding its configuration, mineralized by hydrothermal fluids that have circulated through it for eons. This rock has a history. It has a texture that speaks of time. You run your hand across it and feel the difference. Not smooth volcanic glass, not the freshly fractured basalt of a newly formed surface, but something with layers, with grain, with the subtle topography of a surface that has been altered repeatedly by chemistry and pressure and time. To the west, the sea is real. Not a shallow basin a few meters deep, vaporized and reassembled by each large impact. Not a hydrothermal pool, a body of water that has been here for tens of millions of years, deepening as the crust cools and subsides, fed by rivers of rainfall from the emerging continental masses, connected to other bodies of water by channels carved by the same rainfall that is slowly, relentlessly reducing the carbon dioxide in the atmosphere and cooling the planet. The ocean is 300 meters deep in the place you are looking at. It runs warmer than any modern ocean, reflecting the residual geothermal heat still bleeding from a planet that has not fully cooled. But it is stable. It has been here long enough that something has had time to begin. The water moves. Not from tides alone, though the tides are still significant. The moon has continued its slow recession, is now perhaps 50,000 kilometers distant, its tidal influence diminished but still enormous by modern standards. The water moves because the atmosphere is pushing it. Because the atmospheric circulation that has been developing for hundreds of millions of years is now driving surface currents in the ocean. Because the ocean, for the first time, is deep enough and stable enough to have its own circulation, warm surface water moving poleward, cooling, sinking, flowing back equatorward along the cold, deep floor. The ocean is breathing. Beneath that surface, invisible to you from the shore, the chemistry that has been building for 400 million years has reached a threshold. The exact moment is unknown. It will remain unknown even in the 21st century, one of the deepest unsolved problems in science. But somewhere in the mineral-rich, organically complex water of the early Archean Ocean, a molecule has formed that is capable of catalyzing its own replication. Not life, not yet, but the first molecule that can copy itself. Replication requires two things that were both available in this ocean: a template, a molecule whose sequence of chemical units encodes information that can be read by other molecules, and a catalyst, something that speeds up the chemical reaction that copies the template without being consumed by it. In the 21st century, the leading candidate for the first self-replicating molecule is RNA, ribonucleic acid, a molecule capable of both storing information and catalyzing chemical reactions. The RNA world hypothesis proposes that before DNA and proteins, there was a simpler system in which RNA alone performed both functions, storing information and catalyzing the reactions that copied it. RNA can fold into three-dimensional structures that act as enzymes. RNA can store genetic information in its sequence. RNA can replicate imperfectly, making copies of itself with occasional errors. And those errors, when they produce a molecule that replicates more efficiently than the original, are naturally selected. The first RNA molecules were not designed. They were not planned. They emerged from the chemistry of a warm ocean, the way ice crystals emerge from cold water, by following the chemical rules that govern the behavior of matter at the relevant temperature and pressure. Given enough time, given enough molecular diversity, given the concentrating effect of hydrothermal vents and mineral surfaces and tidal evaporation cycles, given 400 million years of accumulating chemical complexity, the emergence of a self-replicating molecule was not a miracle. It was molecular physics reaching its next equilibrium. Somewhere in this ocean, right now, in a depth you cannot see from where you stand, the most important chemical reaction in the history of this planet is happening for the first time, and it will never stop. You stand on the shore and look at the water. The ocean does not look different. It is brown-green in color, slightly opaque from the dissolved iron and the fine particulates still cycling through the water column. The surface is disturbed by wind, real wind now, organized wind, part of the global circulation system that has been developing for hundreds of millions of years and is now capable of driving waves, shaping coastlines, carrying water vapor across continents. The waves are real. They break against the shore with a sound that is almost familiar. Not quite the sound of modern surf. The chemistry is different, the mineral content is different, the biological life that will eventually transform the sound of the ocean by creating carbonate shells and building reef structures does not yet exist, but the physical mechanism is the same. Wave energy propagating across the surface of a fluid, dissipating against a solid boundary. The sound of it is the oldest version of a sound that will persist until this ocean evaporates, billions of years from now, as the sun slowly brightens past the threshold that no feedback cycle can compensate for. But that is billions of years away. Right now, the waves are breaking on this shore, and the ocean is warm, and somewhere beneath it, the first self-replicating processes are beginning. The sky above the ocean is different from any sky you have seen on this journey. There are clouds, real clouds, dense and organized, towering cumulonimbus structures over the warmer equatorial water, spreading anvil-shaped canopies of ice crystals at altitude, casting shadows on the ocean surface below that move with the wind. There is lightning inside those clouds, the same kind of atmospheric electrical discharge that has been synthesizing organic molecules in the atmosphere since the early Hadean, but now operating in an atmosphere that is slightly less dense, slightly less reducing, slightly more organized in its circulation. The lightning is still building chemistry. 4 billion years from now, a scientist named Stanley Miller will attempt to recreate this atmosphere in a glass flask and pass electrical discharges through it, and within a week will find that amino acids, the building blocks of proteins, have formed spontaneously. He will publish this result in 1953, and it will become one of the most cited papers in the history of the life sciences. The experiment he ran was a crude approximation of what you are watching right now, except the real version has been running for 400 million years. The scale of the result is proportional. You sit down on the shore, on rock that is wet from the spray of the breaking waves, on ground that is neither the burning Hadean floor of your first hours, nor the cooling Archean stone of the last hours of rain, but something in transition, something beginning to accumulate the qualities that will eventually make it a surface where life can live above the waterline. Not yet, but the processes are beginning. Wind carries moisture across the rock. Rain chemistry dissolves minerals from the surface. The dissolved minerals run into the sea. The sea becomes richer. The chemistry becomes more complex. Life, when it emerges fully, will not just inhabit this environment, it will transform it, will produce oxygen that reshapes the atmosphere, carbonate shells that build new sedimentary rock, organic carbon that changes the chemistry of the ocean and the soil, and eventually every geological process on the planet. Life will become a geological force. But it has to start somewhere. It starts in the water behind the waves breaking on this shore with a single molecule that can copy itself. You watch the waves. You listen to the sound of the ocean. The sky above you still has the residual orange of a high CO2 atmosphere, but near the horizon, above the edge of the sea where the haze is thinnest, the sky is fractionally bluer than it has been at any point in this journey. Not the blue of the modern sky that requires an oxygen-rich atmosphere that does not yet exist, but a hint of blue, a suggestion of what is coming. The Rayleigh scattering of sunlight through a slightly less dense, slightly less optically thick atmosphere is beginning to shift the color of the sky toward the shorter wavelengths. The sky is changing color, slowly, over millions of years, but the direction is set. Everything here is pointing in the same direction, toward more complexity, toward more organization, toward life. The same planet that was on fire 400 million years ago is now holding an ocean, and in that ocean, something is learning how to continue. The waves continue to break. The wind moves across the water. The clouds build and release their rain, and the rain runs back to the sea, carrying the minerals of the land with it, adding to the accumulating complexity of an ocean that is, in this moment, on the edge of something that has never happened anywhere in the observable universe, at least nowhere that we have yet confirmed. You do not need to see it happen. You are already here. The fact that you are here, that 4 billion years after this ocean formed, a creature evolved on this planet that is capable of understanding the mechanisms of what is beginning in the water in front of you, capable of narrating the story of how it happened, capable of feeling something in the presence of deep time. That fact is the evidence. The process worked. The cooling worked. The bombardment worked in the brutal, non-intentional sense that a process operating without purpose can work toward an outcome it did not intend. Everything you heard tonight is real. This ocean, this chemistry, this moment, it happened. It is the reason you exist. The waves break. The water pulls back across the rock. The sky is orange and blue and very, very old. You have moved through 4 billion years to reach this moment. You have watched the solar system destabilize and recover. You have watched the sky turn white and the ground shake. You have watched the first rainfall and the first puddle persist. You have watched the ocean form and the molecular machinery begin. And now you are here, at the edge of the thing that all of it was building toward. The sound of the water is very peaceful. The surface is warm beneath your hands, but not burning. The wind is gentle by the standards of everything you have seen on this journey. You can rest here. The planet is still working. It is always still working, will always be still working. But the catastrophic phase is over, and the creative phase has begun, and the two were always the same thing. The waves break, the water moves, the chemistry continues, and you can close your eyes now. The ocean will still be here. It has been here for hundreds of millions of years, and it will be here for billions more. And in that time, it will become the most complex and productive chemical system in the known universe. And every living thing that ever exists on this planet will owe its existence to the water breaking against this shore right now. You can close your eyes. The planet has this. The rock is warm. The water is real. And somewhere in the deep ocean behind you, the first molecule that can copy itself is doing exactly that, slowly, imperfectly, without any awareness of what it is beginning. Let the sound of the water carry you. Let the warmth of the ancient rock hold you. You have traveled 4 billion years to be here. In, out. The waves find their rhythm. And so do you. If this story reached something in you tonight, if the age of it, the scale of it, the strange and specific truth of it helped you rest, please subscribe to Quiet Science at Bedtime and leave a like to help other people find their way here. Good night. Everything you heard tonight is real. This ocean is out there right now, carrying in its water the memory of everything that built it.